Hi everyone. So in this video, we're going to go ahead and start to talk about something called the ideal gas law. Okay, so sometimes when you're solving problems related to gases, you don't have final and initial values. Instead, you just have one set of values. Well, when that happens, you can't use the combined gas law because we need the one values, the initial, and also the two or the final values. We need to see how things change. So what we need to do instead is we use something called the ideal gas law, and that allows us to look at the pressure, volume, number of moles, and the temperature at one specific point in time. So I'm going to quickly go through a derivation of the ideal gas law. I do not expect you to memorize this derivation, and if it's a little bit above your head, that's okay. What I want you to take away from this section is, number one, the ideal gas law comes from someplace. We're not just making random stuff up. And then also, I really want you to know the ideal gas law, what it is. So it's PV equals nRT. So let's see how we get that. So we're going to start midway with combined gas law derivation, where we had volume is equal to some constant times the fraction, the number of moles times temperature over pressure. So the first thing I want to do is we want to multiply both sides by pressure to kind of simplify that fraction. So we end up with pressure times volume equals to some constant times NT. Well, we're going to go ahead and call that constant the ideal gas constant. And we're going to represent it by the capital letter R. So instead of having constant, our equation becomes PV equals nRT, which we oftentimes call PivNert. Okay, kind of adding some extra vowels to make it pronounceable. But otherwise, PivNert or PV equals nRT is the ideal gas law. So that is what I want you to remember. Circle it, highlight it, make sure you know that equation. You will use it a ton, both in this class and if you go on to any future chemistry classes, I guarantee it will make a reappearance. Okay, so that leaves us with the question of what is the value of that ideal gas constant? Well, it's a little different in that it will change based upon what units you're using for your different variables. So if we have things like atmospheres versus bar versus pounds per square inch, we're going to have different values for our ideal gas law constant. However, we're going to base it off of standard temperature and pressure. So standard temperature and pressure, also known as STP, describes the pressure of a gas at 1.0 atmospheres and a temperature of 0 degrees Celsius, which we also know is 273.15 Kelvin. So at STP, we can also calculate that 1.0 moles of gas will occupy 22.4 liters. Okay, so again, some other helpful values to keep in mind there. So what we're going to do is we're going to now derive the ideal gas constant at STP. So we're going to take that equation we had before, the PivNert, and rearrange it for the R. So we divide both sides by NT to get R by itself. Now we're going to plug in those values we get from the standard temperature and pressure. So pressure is 1.00 atmospheres. The volume we know is 22.4 liters. N is the number of moles, which is 1, and the temperature is 273.15 Kelvin. We could also put 0 degrees Celsius, but that kind of messes up with things. So we usually use Kelvin just like all the other times because it works out better for our calculations because we never have negative values. So if we go ahead and multiply those all together, we get a value of 0.08206. Sometimes you see it 0.0821 liters times atmospheres over moles times Kelvin. And again, you're going to be using this value a bunch. So again, highlight it, make sure you can find it easily in your notes. Let's go ahead and apply this information to an actual example. Okay, so let's go ahead and try an example of the ideal gas law. So at what temperature does 52 grams of oxygen, O2, occupy 7.3 liters and have a pressure of 2.2 atmospheres? So if we think about the variables for our equation, we have P, V, N, R, and T. So P stands for pressure, which in this problem is at 2.2 atmospheres. V stands for the volume, which is going to be our 7.3 liters. N is the number of moles, which we don't know that, but we do know that we have 52 grams of O2. So we can go ahead and find the number of moles using molar mass. R is the gas constant, so it's going to be that 0.0821 liters times atmospheres over moles times Kelvin. And then finally, T is our temperature, which is what we are being asked to solve for in this problem. So the first thing we're going to need to do is find the number of moles of oxygen gas. So we're going to set up our factor label table. So we have 52 grams of O2. And then we need to find the molar mass of oxygen gas. Well, one oxygen atom has a mass of 16. So for O2, a mole of that would have a mass of 32.0 grams per 1 mole. If you need help with that process, make sure to look back in your notes to when we first talked about molar mass back in Unit 3. Okay, so we're going to go ahead and divide because we have one number on top and one on the bottom. So that gives me a value of 1.625 moles. And for right now, I'm going to keep all of those numbers. I'm not going to worry about rounding sig figs. I'll do that in my last step. Okay, so otherwise for our equation, we have PV equals N, R, and T. And we want to solve for the T. So I'm going to go ahead and rearrange the Pivnard equation to get T by itself. So I'm going to divide both sides by N and R. Okay, so that gives me the equation T is equal to pressure times volume divided by the number of moles times the gas constant. So from here, I just need to go ahead and plug in my values. So for our pressure, we have 2.2 atmospheres. For our volume, we have 7.3 liters. For the number of moles, we now know that that's the 1.625 that we found. And then the gas constant is that 0.0821 liters times atmospheres over moles times Kelvin. Okay, so once we have that, we're going to plug that into our calculator. So we're going to take 2.2 times 7.3, and then we're going to divide that by the 1.625, and then divide that again by the gas constant, 0. So that gives me a value of 120.4. And the unit for that's going to be Kelvin. The way I figure out my unit, I see what cancels out. So atmospheres cancels with atmospheres, liters cancels with liters, moles cancels with moles, which leaves me Kelvin for my temperature, which does make sense. Now, final thing, I want to think about my sig figs. This has 4 sig figs, but for all of my givens, I only have 2. So my final answer for this one, I'm going to round to 2 sig figs, is going to be 120 Kelvin. Okay, so the next question is a you try. So this one says, you fill a 25.0 liter rigid metal container with nitrogen gas. When you're done, the container has an internal pressure of 75.0 atmospheres at 28.0 degrees Celsius. How many moles of gas did you add? Assuming the container was completely empty to start. Okay, so you can go ahead and use Pivnard. One thing I do want to remind you about, this is in degrees Celsius, and the Pivnard equation, the ideal gas law, uses Kelvin for the gas constant we have. So make sure you convert that. Otherwise, go ahead, pause the video, try this out on your own, and then come back and check your answer. Okay, so let's go ahead and start by writing out our variables. PV equals N, R, and T. Our pressure is 75.0 atmospheres. Our volume is 25.0 liters. N, that is our unknown. That's what we're trying to find. R is the gas constant, always the same for those variables. Liters times atmospheres over moles times Kelvin. And then temperature, remember I have to convert that into from degrees Celsius into Kelvin. So I had 273 to the 28, and that gives me a value of 301 Kelvin. So now we just need to go ahead and rearrange our equation. So PV equals nRT. I want to get the N by itself. So I'm going to divide both sides by the RT. So my rearranged equation, N is equal to the pressure times the volume divided by the gas constant times the temperature in Kelvin. So let's go ahead and plug in our variables. So N is equal to 75.0 atmospheres times the volume, which is 25.0 liters, divided by the gas constant, 0.0821 liters times atmospheres over moles times Kelvin. And then finally our temperature, which is 301 Kelvin. Okay, so if we look at this, for our units, atmospheres cancel out, liters cancel out, and Kelvin cancels out, leaving us with moles, which is what we want for N. So now we're going to plug this value into our calculator. So 75 times 25 divided by 0.0821 times 301. So that gives me a value of 75.87 moles. But again, I want to think about my number of sig figs. So I have 3, 3, and 3. So I need to round this to 3 sig figs for my final answer. So I'm going to chalk this off between that 8 and the 7. 7s are greater than 5, so they round up. So that gives me 75.9 moles of gas that are added. So I hope that helps. If you have any questions with ideal gas law, please let me know. Otherwise, have a great day, everyone. Bye.